Okay, welcome back everyone. So today I'm going to be doing a quick video, and it's actually going to be covering the following problem. Oh, and by the way, I have a different setup here, so I'm using a different whiteboard, and the reason being is that this one is a bit more stable, and I prefer this better because I don't have to like lean down whenever I don't have to bend down whenever I have to, continue using the other whiteboard. I will still probably be using the other one in videos, but I'll probably be alternating. Um, so here's a problem, and I actually got this problem from this YouTuber named FunMaths. I'll link his channel in the description, and I realized I came up with a faster solution than him, in my opinion, or at least I think it's a bit more interesting, and that involves some concepts uh, in modular arithmetic. So what we're going to do here, and I'll read out the problem, find all solutions to n to the r minus 2 equals k factorial, where n, r, and k are natural numbers, where r is greater than or equal to 2. Okay, so, well, what I want to start off with is let's first consider the cases where r is even. And the motivation for this is that we have some nice properties with, and we're going to take the equation mod 4. Since we also have this factorial, we're also going to consider k's that are greater than or equal to 4. So it's just that the right-hand side will be 0 mod 4. And then we'll consider cases where the power of n is odd and even. And like I said, basically, the thing about even powers mod 4 is that, or perfect squares mod 4 is that the only residues that they can take up are 0 and 1. So let's just consider this equation mod 4. So we'll consider the first case. And here we're going to take k is greater than or equal to 4. And we're actually going to show that no solutions exist where k is greater than or equal to 4. So we're going to take case 1. So case 1 is going to be where r is equal to some, let's say 2n, where n is going to be some positive integer, right? So, well, if we plug this in, we're going to get that n to the, oh, I probably shouldn't use n. I should use n, since we're already using n. So we have n to the 2m is equal to k factorial plus 1 plus 2. So if we reduce this mod 4, we're actually, since k factorial is greater than or equal to 4, it's always going to be multiple of 4. So we have that n to the 2m is congruent to 2 mod 4. But this is a contradiction since this is a perfect square, and perfect squares cannot be congruent to 2 mod 4. So this is a contradiction. Let's go to our second case, and that is where r is equal to 2m plus 1. And since we're dealing with different cases, we don't have to worry about these limitations overlapping. So in that case, if we reduce mod 4, we're going to get n to the 2m times n is congruent to 2 mod 4. Okay, well, let's see. So again, the only possibilities for this one is 0 and 1. It can't be 0 clearly, otherwise it won't be 2. In other words, it has to be 1. But if it's 1, then n has to be congruent to 2 mod 4. But then that would directly imply that this is going to be congruent to 0 mod 4. And that's, again, a contradiction. So this case also results in a contradiction. In other words, this entire case is results in a contradiction. So that tells us that k is strictly less than 4. Okay. Well, now we can just quickly find all our possibilities. We just have well, when we just have that, like, for example, when k is 1, well, we have n to the r is equal to 3, but notice that this is impossible, so k cannot equal 1. When k equals 2, we get 4 on this side, so we have n to the r equals 4. So in other words, we get the solution n r clearly 2 to 2 is 4, NR, and then we have our K here. It's just all 2's. Okay, and finally, let's consider K equals 3. If K equals 3, we're gonna get 8 equals n to the r. And it's easy to see that the only solution here is n equals 2 and r equals 3. So in other words, we're just going to get the solution 2, 3, 3, right? So in other words, these two solutions exhaust all our solutions, and that finishes the problem. So hopefully you enjoyed that, and have a nice day.